Hello everyone and good morning. First of all, thank you all for being here today. I'm very happy to present my master thesis titled Semantic Asset Administration Shell for Circular Economy. Just as a first notice, you would see probably the slides. There are 100 slides, but I only have 20 minutes, but you can also go through your own pace. I won't explain all the slides, of course. This is the outline of this presentation. I will start with some background information. Here we talked about the circular economy, and in order to realize this shift from linear economy to circular economy, one of the key enablers is digitalization and more precisely interoperable digital twins. So the current waste sorting process is not efficient. So we have a waste stream, we simply shred it, and then we separate metals from other materials with some magnets, and then we melt the metals and burn the rest. So that's why the resource project started with the goal of improving the efficiency of material recycling by combining digital twins and artificial intelligence. So within this project, the idea is to use the concept of digital product passport. So we want to have a digital representation of our products, which is an interoperable standard digital twin that is called asset administration shell. This is a critical aspect because proprietary systems are not suitable solutions. So the case is sorting electronic waste in this project, and we have some information models based on asset administration shell, which you can see an example of it in the picture. And here you can see the pictures of a pilot sorting facility of our project partner, Fraunhofer IWKS. We can see different electronic waste, printers, cameras, mobile phones, smartphones as the input of the system, and based on the device model that the machine learning algorithm detects, we fetch the information that are in the digital twin from a cloud-based solution, and based on the sorting parameters that we have, we separate waste into different containers. But here we can apply a couple of enhancements. So for example, as a recycler, I would like to know how much gold, silver, or aluminum I would yield from the devices on the right container, for example. Or I want to know how old these devices are on average. So these are some possible questions that you might ask, but there is also another problem here, and that is the two attributes that we have here. Being dangerous and valuable typically would be computed based on the value of other attributes. So a product is valuable to recycle if it contains more precious metals than a specific threshold, but that also depends on the perspective of stakeholders because we don't have one single waste treatment method. So this threshold and these criteria would depend on the stakeholder. So with our cloud solution, we want to have a data-centric approach. Digital twin is everywhere, we use it everywhere, and we want to have a smarter and configurable and individualized decision-making. So for example, the user might pay more for a device to ensure that it will be recycled using a high-tech, environmentally friendly methods that is more expensive. So now we can establish our research question, which is, can semantic technologies help a non-expert user to query the asset administration shell without dealing with the implementation details of AES? And to answer this, we keep in mind our use case, which is around the recycler. So how can a recycler, based on predefined rules that he or she defines, find valuable or dangerous products, for example? This is, of course, an example. We don't want to create a hard-coded custom solution at the end. So we want to have a generic solution. So one part of the question deals with querying the asset administration shell. So let's formalize the queries a little bit so we can know what type of behavior we should expect. In the first query, we have a list of products, and we want to see all the products containing attribute A, followed by criteria C for that attribute. You can see the set notation here, but the example is clear. So here the attributes that the attribute that we desire is the amount of gold, which is part of the digital twin, and the criteria is a mathematical predicate that is more than 7 grams, for example. And on the right, we can see the filtered elements that indicate valuable products. But obviously, we don't want to be limited to only one attribute. We want to have different attributes, combine them logically using different logical operators. And also, we don't want to filter just information. We want to also update our digital twin dynamically and add and assign new attributes to the digital twin. The other aspect is about non-expert users. So our stakeholders in circular economy, they have no idea about RDF, knowledge graphs, even AES. So we need to know what are the possible approaches to hide this complexity and make the process easier. So regarding the state of the art, here you can see a summary of the most relevant state of the art. Sebastian Bader did the initial work and created the RDF representation of AES. Almost all publications use the version 2 of the AES. Here we use the version 3, which is the recent version. Regarding the knowledge graph construction, people use RML. Initially, we also started with RML. However, RML is not suitable for complex recursive structure of AES, and we want to also convert RDF to JSON. With RML, you can only convert JSON to RDF. So for that, we need a custom parser and serializer and deserializer. And in this work, we introduced the first generic solution that works for the version 3 of the meta model. And similarly for searching the AES, only one work mentioned to use Neo4j and Cypher as a query language for AES, and other solutions are mostly hard-coded and task-specific. And regarding the reasoning on top of AES, only one work mentioned the combination of RDF and spin rules, but spin rules are outdated, and also we don't have a clear workflow for complex rule-based reasoning. So in this work, we use a well-known framework, Apache Jena, for rule-based reasoning. So these are the main components that we have. We work with the RDF representation that forms our knowledge graph. We can use the schema to validate the content of this knowledge graph for data quality assurance. And we can optionally combine this knowledge graph with other semantic models and perform reasoning on top of it to infer new knowledge. And we want to be able to query this information and use a web application and some user interfaces on top of it to, at the end, fulfill our use case. So this is the typical JSON representation. This is a submodel. We have a property and a value for that property. So most people work with this JSON representation. This is the RDF representation. This is the official representation that is part of the specification. We have the same information. The conversion between RDF and JSON is lossless, but it looks a little bit weird in the first look. We use RDF as a representation method because we have a standard query language, which is Sparkle. We have open source tooling available like Apache Jena, and we have also commercial tools available like AWS Neptune. We can do query federation, which is a nice attribute, and the most important factor is that the RDF representation is part of the specification, so we don't need to design any database schema or anything for that compared to other approaches. For the use case and the data, we take one submodel that's developed in the resource project, and we instantiate the data with some random values. The content of this submodel is here. You can see that there are some attributes, and there is the submodel collection that contains the material composition. These are the EU critical raw materials, in addition to some precious metals. So these are the components of the system. Of course, we don't focus on all the components. We can't implement all the components, but we have a knowledge graph, and we store everything in an RDF format that include the AES and maybe other semantic models. And we have dashboard, semantic reasoner, semantic search on top of it. And this semantic bridge acts as the parser would be included in the semantic bridge to deal with the RDF and JSON representation, as well as validators. So for data quality assurance and validation of input data, we want to be able to capture inconsistencies and maintain the quality of the data. And Shackle is the most suitable choice for complex cases. So on the top, we have a simple case we say that the price is a mandatory field and the user should provide it when he is or she is creating the submodel, but there might be co-occurrence constraints. So the constraint depends on the value of another field. For example, here, if the city is Berlin, then the price should be more than 200. So this is a complex scenario, and for complex scenario, Shekel is the most suitable choice. For the knowledge discovery and search, we have this SPARQL query that satisfies the query number 1. In the first part, we want to go from the AES to submodel, because AES or shell does not hold the submodel information or the data. It just contains a link to the submodel. So here we need to follow that link in the knowledge graph. So that first part is regarding that. In the second part, we get the submodel, we get the semantic ID of the submodel, and we need to be sure that semantic ID match. We can use a regular expression or exact matching method. And when we know that we have the submodel, we can consider all the properties inside it, or all multi-language properties, or whatever that we want. And we can filter the values or filter the ID short to target specific properties. And we apply our predicate here to filter the information. But we wanted to have multiple attributes. So the first part of the query is same as before. We want to link and go from AES to submodel. This part is very important. I will explain it later. For the first attribute, we can get it in this way. For the second attribute or other attributes, we can have our conditions here, and then at the end we can apply a complex predicate on top of these values of these properties. And we want to be also modify the knowledge graph. So with the SPARQL insert and update and delete, we can modify the knowledge graph and insert new triples. So here it's similar to the query 1 and 2 that we had. We can construct some new variables here to use it in the insert clause. And in the insert clause, we create a property and we add that property to submodel. So that happens dynamically. So we have all the rule-based reasoning. We use Apache Jena rule syntax. So these are the prefixes that we use, other semantic models that we can include. This is the name of the rule that we have. There is a if part. So we say that the temperature, if it is more than a value, then there is a consequence. The consequence is to add a new property to the digital twin, but we can also include other semantic models. So here I'm using the characterization methodology ontology. Different types of hazard is defined there, and for example, I can link the submodel or AES or asset to these types of hazard. So we have a dashboard. The dashboard was part of the resource project, but I expanded this dashboard and added some pages. So this is the home page view that you can see the available digital twins in the platform. Here we have the video that you can see, so the user can log in the system, and with the home option, you can explore the digital twin and see the details of them. So you can expand the submodel collections and see the material details here, for example. And using the search engine tab, you can use the pre-existing queries that is based on the profile of the user. So here we have the recycler. So we have the related queries for that, but you can also modify the queries if you know how to do it. We also have a simpler user interface for knowledge discovery that is in the knowledge discovery page. So here we have different rules. There is a different user interface for that. So you can create or select your property that you want and apply your condition you desire, and then combine them using different logical operators, group them, and then you can execute the search button, execute the search with the search button. And on the background, we will generate a SPARQL query, which is depicted here. So on the background this happens. Here we show it as a prototype. That's what happens in the background. And on top of it, we can also explore our knowledge graph. We have a dashboard that you can navigate through the graph, expand the nodes, and see the values of them. So that could be also another way to explore the knowledge graph that we have. So we did also some query performance benchmarks. For that, we generated some sample models. So we can see some basic information here. We randomly generate different sizes of data sets from thousands of triples to millions of triples. And for the benchmark, we have some sample workloads. So the simple workload is to filter based on temperature. The aggregation operation is to aggregate based on the location, the temperature based on the location of the robots that we have. And we also have on-the-fly unit conversion that is using the QEDT ontology, measurement ontology in the background to compare kilogram and gram. So if we have a query for that, we can do the unit conversion. So the benchmarks are on a normal laptop, so it's not an isolated or a formal benchmark. We are using Apache Jena. The results are averaged on 10 runtime. We can see on a small size data set here, the response time is pretty constant and acceptable, but when we go to millions of triples and above 2 million triples, then we would have a hard time on this configuration, but on a small size data set, it works fine. For rule-based reasoning, we also did the similar benchmark. It takes a lot of time to load the information from the disk, so it is very time consuming. It's in seconds, so almost 2 minutes. And also the rule-based reasoning happens in memory, so we require 4 gigabytes RAM for that. But in exchange, the rule-based reasoning happens in memory, so it is very fast, and we can reason almost instantly, depending on how much rule and how complex are the rules. There is one particular issue with the current RDF representation. The current RDF representation doesn't maintain the order of the elements. So in that sense, we will lose the order of the elements that are important. So for example, for reference element, this ordering of the element is important. This is an open issue, and in order to solve that, there is no single best solution to maintain the order of elements in RDF. But here we use AES index as depicted here, which is also a nice approach to have here. And the benchmark that we do here is not really large scale data. Also, other available benchmarks are also in the same order, so we don't have any large scale benchmark available. And we cannot really judge the result because there is no query performance benchmark available. But with the data set that we create here, we will publish it, and then it would be possible to have some benchmark in the future. And for sure, reasoning for now is suitable for a small size data sets, but there are some ongoing research to use, for example, Apache Spark for distributed old reasoning or rule-based reasoning. Regarding the user interface and user experience, we didn't perform any user study to measure how much effective are these user interfaces, but for sure the user wouldn't need to deal with Sparkle or the query language, so the UI will fulfill that. But this is an example prototype based on ongoing project, SPAR Natural. So maybe in the future we can also expand this, so we can probe the knowledge graph and make the property recommendations, so make the UI nicer and easier to work with. And I want to highlight the contribution of this work. So this is the first semantic solution that uses the official RDF representation of AES, the version 3, the implemented parser that does the conversion between JSON and RDF. And RDF to JSON will be open source, which is a great contribution. This will be the first tool, in fact, and also one workshop paper published so far, and we will also in the future publish the dataset and benchmark dataset and other resources. And there were also, as a side artifact, different open source contribution in Eclipse Basics, Eclipse Basics Python SDK, ASX Server, and Package Explorer. So as a side artifact. And for the future works, it would be nice to further explore these performance aspects. We can, of course, enhance the user interface and do user experiments. One combination would be to combine large language models, ChatGPT, with knowledge graphs. They are a really nice combination. So in the future, we can have this knowledge graph verbalization to explain the digital twin to the user and have conversational user interfaces. And regarding this query feature, we can introduce a new query language, only specific to asset administration shell, to query asset administration shell, which is can be called ASQL. And finally, yeah, thanks again for being here, and thanks to my supervisor and all my colleagues for supporting me through this process, and also thanks to my family. My wife, my parents, and my brother, and my sister for all these supports. These are the references, and these are the list of questions that you can ask, so we can have a discussion, and you can go through the slides and see what's going on.